Assalamualaikum warahmatullahi wabarakatuh. Okay, now we continue in topic piping system. Okay, so no piping system is also include the energy line, okay, and also the hydraulic grade line. Okay, energy line EL shows a total head for a certain cross section in a system. Okay, EL here. So, and hydraulic grade line it shows piezometric head for a certain cross section in system HGL here. So we have learned that this line and the energy line and also the hydraulic grade line here. Okay, this is energy line and also the hydraulic grade line here. So we have learned that equation in chapter 3 and chapter 4. Okay, we learn in Bernoulli equation. Okay, now we also use the Bernoulli equation in this topic. Include the HF plus HM. Okay, so this is the example here. Okay, EL and HGL. So EL and HGL. So this is water flows from tank to atmosphere. Okay, this is the example here. The blue line here. Okay, and also the red line here. So this is shows about the energy line and also hydraulic grade line here. Okay, so this example 1. So example 2, when they have two tank, okay, from the point here to the point 2 here, okay, they have two tank and also have the turbine here. Okay, so you draw the energy line here, okay, and the dot line here, red line here, so the HGL. Okay, so when we have the turbine, so automatically the both line here drop here. Okay, this is called the H turbine, head loss of turbine here. Okay, so you sketch the EL and the HG line like this one when we have the figure of the two tank and also. Okay, example 3, when fluid flows through a nozzle. Okay, when fluid flow from the nozzle here, so velocity increase when there is a contraction, okay, in diameter of pipe. So automatically the EL like this one increase, okay, steady and increase at this part here. But for the HGL, automatically the increase like this red line here, because this is example 3 4, fluid flows through a nozzle. Okay, so this one example 4. So draw the EL and the HGL line when water flows through two types of diameter pipe. Okay, they have one pipe and pipe 2, pipe 1 and also pipe 2. Okay, so you draw the EL line, the blue line here is the EL when stop at the contraction here from the pipe 1 to the pipe 2 here, so HM is drop here, okay, and until at this part. But for the HGL, so at this part the red line here is increase, okay, so increase, so the line is and to the nozzle here is decrease. Okay, so this is look like for the water flows through two types of diameter pipes. So example 5, we have used two pump and also the turbine. So the both of line EL and the HG line is like this one. If in pump, so this is increase. Okay, at this part at the turbine, so the line is decrease. So the drop here. Okay. So we use the Bernoulli equation. Okay, so energy okay, the Bernoulli equation here, so you use as we learned in chapter 3 and chapter 4. So in chapter 5 we also use the equation, the same equation, but if we have used the pump and the turbine, so you use this, the head loss in pump. Okay, pump here we put the here. Okay, okay, and also HL is energy head loss. Okay, HL is mean for the HF and also the HM. So this we cover in chapter 4. Okay, HL chapter 3 and chapter 3 we cover the equation here. Okay, HL we cover in chapter 4 and we use the H pump and H turbine in this chapter 5. If we see the pump here and also the turbine. Okay, so EL and the HGL. Okay, actually this is the explanation about the EL and the HGL. So you can explain using this if in your finals ask you to list down between the EL and or the HGL. So EL is always higher or same level with HGL. So the difference between two lines is the value of kinetic energy head. Okay, major losses cause EL and HGL to decrease gradually. Okay, minor losses cause EL and HGL to decrease rapidly. Okay, so major losses, okay, cause EL and HGL to decrease gradually. Okay, if the minor losses is cause EL and HGL to decrease rapidly. So if we use of pump, line increase immediately. When use of turbine, lines decrease immediately. So this explanation is referred to the figure, the example 1 to example 5. So we can explain about this one. Okay, this is refer more on the figure from the previous slide. The flow is this one. Okay, at the entrance here. Use the 0.5 V squared over 2G. Okay, so HM is they give you the K. Okay, the K of the pipe. Okay, the friction coefficient of the pipe. So we use the 0.5. Okay, from this equation, so we convert to this equation here. HF is VB squared over 2G. So and we just put here. And we use to get the ZA minus by ZB OHS. So this equal flow to atmosphere. So we use the Q is equal to A 2G HS by Y K. Okay, so example 5.1. So this is water flows to the atmosphere. Okay, same the figure same as the previous slide. Okay, determine the discharge. So these questions ask you to find the discharge. Okay, discharge of water flows in the system. Okay, so we have the A and to the B here. Okay, we have the length of 100 meter, diameter of 0.5 cm. So the F, they give you the F is 0.005 and the HS is from the point A to the point B 10 meter. So we use that the V, okay, taken from the previous slide. Okay, so this is the K. Okay, so just put all the parameter in these questions. HS is ZA plus ZB. Okay, 10 cm. F 0.005. L 100. D 0.5 cm. K. Okay, from this one K 1.5 plus FL over D is equal to 1.5 plus. Okay, so you just calculate to get the K. Okay. Okay, so we get the velocity. Okay, after we get the velocity, we put the velocity insert to the Q. So we get the value of discharge. Okay, so this is calculations to get discharge. Okay, so in chapter 5, we have learned in chapter 3 and chapter 4. So we use the equation from that chapter. We use in this chapter 5 in analysis in pipe. Okay, so example Okay, we have the entrance here. Okay, and the submerged discharge here. Okay, so we have this one is 0.5, this one is 1. Okay, the small k. Okay, the small k for this fitting of the pipe. Okay, so we use this one. Okay, 0.5 and also 1 here. So this is for HF. Okay, so this one for HM and this one also for HM. So this is HF. Okay, so we get the, okay, from this we just go through this one, so we get ZA is HF. Okay, so we just only have the VB here. Okay, so the velocity is VB. Okay, because at the right side, so we have the VB squared over 2G 0.5 plus FL, okay, D plus 1, okay, from this one. So we just get here, get this equation because the previous slide, so we let assume as the K. So this is the K, big K. Okay, just correct your notes. Okay, so we have the Q is equal to AV, so this one. Okay, to find the discharge and determine the difference level. Okay, the difference level between two reservoirs which is connected by single pipe of cast iron. So the example for 5.2, we use the figure, the previous slide figure. So we just solve the equations, put the value here, and we get the velocity. Okay, after we get the velocity, so we use the Reynolds number. Okay, this is Reynolds number. Okay, just correct here, just using the Reynolds number. So we get the turbulent here. Okay, so and we get the relative roughness here, E over D, we get the 0.005. Okay, so we get the F from Modi chart, so we get the F is 0.03. So you put the F here to the K here, so we get the value of the K. F is from this one, so we get this 601.5 Modi chart to get. So you get the velocity here because we get the K from the previous slide. Just put the value here and then you get the HS. Okay, HS is actually for the value of ZA minus by ZB here. Okay, so we get the value of HS here. Okay, this is an example for 4 or 5.2. Okay, so non-rigorous head loss equation. So we use the empirical equation, which are Hazen-Williams, Manning, and Darcy-Weisbach. So this chapter we using for your project. Okay, so this is, we must learn that using the Darcy-Weisbach here to get the HF. Okay, so IN2 here. Okay, so the K is the coefficient, the small k is the coefficient to get the, using the Darcy-Weisbach and using the Hazen-Williams. So this is the equation and the Manning. Okay, so this is the two non-rigorous head loss equation. So as we can see that HF is the K. So K is from this. Okay, K is, okay, so again no need to confuse that this value of K is only for this one and for this one, for this one. This means if in your questions the K is given for the Darcy-Weisbach, Hazen-Williams, and Manning, so the K value in this equation is this one. Okay, the 3 here. Okay, if in question ask you to using the Darcy-Weisbach, so you use the K, this one. Okay, if you use the Hazen-Williams, so you must use the value of K, this one. Okay, in this one. Okay, so you must find the Q total here and HL here, the value of this one. Okay, try to solve. Okay, this we have just the short solutions of this one. Okay, so you try. This is expansion. Okay, so we have one entrance, we have HF1, we have expansion, we have HF2, and we have the exit. So we have the head losses 1, 2, 3, 4, 5. Okay, 5 head losses in. So we just table the calculation. We just using the table here, just table to get the calculation. So the entrance, okay, the head loss for the entrance, head loss for the fluid friction in H1. So head loss in expansion, head loss in fluid friction HF2. So this is HF2. This is HF1. Okay. This is entrance, this is expansion, this is exit. So you just total here. Okay, for entrance, H entrance, we know that 0.5 V1 squared over 2G. Okay, you just solve the equation here in terms of V, okay, in terms of V2, okay, because we know that the continuity equation here, Q is equal to A1, V1 is equal to A2, V2. Okay, so we know that the we don't know that the velocity 1 and also the velocity 2. So we use the velocity 1 in terms of velocity 2. Okay, so H1 entrance, we have the V2 1 here. So you just put the velocity 1 here to this equation. So we get the 0.5 times by 2.89 V velocity 2, okay, squared over 2G. So we get the 4.44 V2 squared over 2G. Okay, so we just get the H entrance here. So we get the HF1 here. We just put all the value here because we use the 0.01. Okay, L length of the pipe 1 is 6. So this is using the V1, put here and put the G and also the diameter. So we get in terms of 3.34 V2 squared over 2G. Okay, so expansion, so we use the expansion here. You just use the chapter 4. Okay, chapter 4 using the expansion. Chapter 3 and also chapter 4. Okay, so because they has used the HM. Okay, so HM for expansion, so V1 minus by V2 squared over 2G. Okay, so you just put the value here. So all the calculation is in terms of velocity 2. Okay, so we get this one HF2, okay, in terms of V2. So and also V2 here exit, okay, V2 squared over 2G because the exit is the 1. Okay, sharp. Okay, this entrance 0.5, the exit is sharp. So this is the 1. Okay, so we get, you see, just total up of this one HM. So we get the 12.94 V2 squared over 2G. Okay, in terms of this one. Okay, so after that you use the Bernoulli equation. Okay, use the Bernoulli equation from 1 to 2. Okay, so we get this one because this is the open to the atmosphere, so this is 0. Okay, V squared also 0 here. Okay, so the velocity 2 also 0. So we just use that. Okay, so it's not 0, so they have Z2 here. Okay, so Z1 minus by Z2. Okay, or Z1 or ZA or ZB here. So we get this 6 here. Okay, so HL, total HL is you calculate from the table previous slide. So we get the 12.94 V2 squared over 2G. So we get the velocity 2 is this value. Okay, after we get the value of V2, so you just put to this equation A2 V2, so we get the Q, okay, the discharge in the pipe. So, and after you get the V2 and get the Q, so you solve this equation. Okay, so V1 is equal to 2.89 V2, so just solve this one, so we get the velocity 1. Okay, so this chapter we use Bernoulli equations, we use the HL and HM. Okay, in chapter 3 is not include the HL. Okay, in chapter 4 this include the HL and the HM. So HM plus HF is HL. So this chapter 5 we use the equations that we use in the chapter 3 and chapter 4, but we solve it in using the pipe in series. Okay, so this calculation for pipe in series. Okay, that's all for the type in series. So this is the figure that we use. Okay, I draw in the previous slide, so draw here. So after you get the value, so you must, because in the question asks you to sketch or draw the EL and the HGL, so you just draw the EL line and the HGL, because we know that between the two reservoir and the difference pipe expansion from the small to the bigger pipe, so the EL is dropped at this pipe and the HGL is increased at this pipe. Okay, so that's all for the sketches of EL and HGL. Okay, these questions is used in this is actually the questions in final previous semester in 2009 2010. Okay, so like this one, the questions for final. We look the pipes in parallel. Okay, pipes in parallel, we have 1 2 3 pipe, but we put the parallel here. Okay, parallel 1 2 and 3, so this is called the selari. Okay, maksudnya ABM, pipe yang disambung secara selari. Okay, yang first tadi pipe yang disambung secara siri. Okay, bersambung secara siri. Yang ni pipe yang disambung secara selari. So this is called pipes in parallel. So we have the A and the B. Okay. So for the parallel or looping pipes of the following figure, the continuity and the energy equation provide the following relation. Okay. So this using for pipes in parallel. Okay, Q is equal to Q1 plus Q2 plus Q3 and so on. HL is equal to HL1 is equal to HL2 is equal to H3. But for the series, Q is Q1 equal to Q2, Q3 and so on. And HL is HL plus HL1 plus HL2 plus HL3. That's for pipes in series. But this equation for pipe in parallel. Okay, so this is because pressure A and B are common to all pipes, so this HL is equal to all pipe. HL1 is equal to HL2, HL3. Q is total Q is just plus Q1, Q2 and Q3. Okay, plus the all then. Okay, because this is pipe 2 has a length 4 times longer than pipe 1. Okay, so pipe long at pipe 2 is 4 times longer than, so that's why we get the L2 over L1 is 4. Okay, so actually long at pipe 2 is 4 longer than pipe 1. Okay, so L2 is equal to 4L1. So we get the L2 over L1 is 4. Okay, from this one, so we solve this equation to get the velocity. Okay, So velocity is 2 squared over 2GD. So we get the L here, this one. Okay. So we know that the Q is, okay, Q is this one. Okay. Q is 1. Okay. Q is 1. Okay. We know that the Q over A1. Okay. But we know that the V squared over, okay, V squared is this one. Okay, so you just to get the V1 squared. Okay, so you get the velocity 27.3 meter per second. Okay, from this equation, we know that this one, okay, to this one. Okay, so we get the this one. Okay, from this one. Okay, from this one, and the L1 and L2 just put to this one, so we get the velocity 1 here. Okay, because we know that the L, the L2, and we know the F. Okay, F is given, so you just solve these equations, put this equation, and we get the velocity 1 here. Okay, so after we get the velocity 1, so we know that Q1 is equal to A1 V1. Okay, using this equation, we get the Q at pipe 1. Okay, so we get the Q at pipe 1. So last, we just total up the Q in that pipe. So Q total is equal to Q1 plus Q2. So we get this equation. Okay, so we just do the example. Okay, so this is example 5.10, but this is in feet. Okay, the length is in feet. Okay, you try to solve this example, but you change the length here. Okay, just change as the meter here. Okay, so just change the feet. So you must change the value of 2000 feet to meter. Okay, 106,000 feet to meter. Okay, this value, okay, this value, try to change, convert feet, okay, to m, okay, to m, to meter. Okay, you just try to solve this one. Okay, so just solve the feet to, okay, this is also the feet, the value of this feet. Okay, you just change to meter. Okay, change to meter. Okay, try to do this solution of example 5. Convert the value of feet to meter. Okay, meter or mm. Okay, try. So okay, after we get here, we can discuss in the next week. Okay, before your test. Okay, so actually this is just for knowledge, your knowledge, because these questions, they have combined from parallel pipe and series pipe. Okay, so this is the solutions. Okay, you try to solve, we change the value of feet to meter. Okay, I also have the solution to this, okay, these questions. Okay, but I want to you try to do first. Okay, so we look at the pipe network. Okay, so this pipe network is include in your project. Okay, because the pipe network is not covered in your final. Okay, so they have no questions for pipe network in final. Okay, because you have do the project in this pipe network. Okay, so in final, for chapter 5, they just only have the pipe series, pipe parallel, and the previous. Okay, the previous slide from pipe parallel and pipe series. Okay, that's all. So just important thing, you must know that you must use the Bernoulli equations, okay, and also use the HF and HM, okay, for the head losses. Okay, when in question mention that they have no minor losses, that mean they have no HM. Okay, if in the other question mention that they neglect had losses, so if neglect had losses, so they have no HL. Okay, so neglect minor losses, no HM. Neglect had losses, no HL. Okay, that's all. Okay, if no HL, so they have no HF, and also they have no HF. Okay, so we look at the pipe network here. Okay, so this pipe network, so you can also look at the YouTube also on to how to find the discharge in this pipe, because this is using the rangkaian, maksudnya rangkaian pipe network. Okay, so the distribution pipe system are frequently interconnected so that the flow to a given outlet may come by several different paths. Okay, as a result, we often cannot tell by inspection which way the flow travel, as in pipe BE. Okay, so from flow, from this is inlet. Okay, flow inlet. Okay, this is flow outlet. So outlet. Okay, so I just put the O outlet. So this is outlet. Okay, this is inlet I. Okay, so in this pipe network, we know that I is symbol for inlet. Okay, O is symbol for outlet. Okay, so you just, okay, there are three simple methods to solve for pipe network in loop configuration. So we have three methods, okay, to solve this pipe network. Okay, Hardy cross. Okay, Hardy cross, we using either Darcy-Weisbach or Hazen-Williams equation. Okay, so in this project, actually, we use the Hardy cross. Okay, in this project, for your project group, we use this Hardy cross. Okay, so Hardy cross is using either Darcy-Weisbach or Hazen-Williams. So in your project, if in your group this mentioned that you use Darcy-Weisbach, so you use the equation for Darcy-Weisbach. If you use the Hazen-Williams equation, so you must use the Hazen-Williams equation. Okay, so the most popular is Hardy cross method, okay, which involve a series of successive approximation and correction to flows in individual pipes. Okay, so the most popular is Hardy cross, because we can use the Darcy-Weisbach or Hazen-Williams Manning here. Okay, so use the Manning to get the HF using the Manning. This one, so 2, this is negative, so this is 2. Okay, so if this is 2, so you must total up the from the 60 to 40, 60 and 40. So this is just have the 2 and if the 9 here. Okay, so you just, if the 9 is negative 9, this is for the second correction. So you must plus the 60 plus 2, 40 minus by 2. Okay, so you get the new flow, in the pipe. Okay, after first correction. Okay, so you just solve the value here until you get the 2 here and the right loop here, so we get the 0. Okay, they have the 0 here. Okay, if the 0, we have the discharge, the flow discharge here, just the right value. But this one, so you must, this is positive 1 at the second correction. After second correction, so you just get this. Okay, because this just only have one loop. Okay, because from this one to inlet to outlet and the outlet, so they just only have one loop. Okay, Okay, so if they just only have one loop, so you just use the one. The calculation is the table is just only for one loop. Okay. Okay, so this table only for one loop. If you have 2 or 3 loops, so you must show that you can just put the table here, just try loop 1. Okay, this is calculation for loop 1. Okay, if you have loop 2, okay, so you just calculate the other table for loop 2. From loop 1, loop 2, loop 3 or loop 4, they have 2 loop or 3 loop have the small value as this the q. Okay, the data q is have the final 0.000 something, okay, until you get the value of small q. Okay, so you can stop. Okay, that's the calculations how to solve your project group, okay, using work. Okay, that's all. Thank you. Okay, until you have any questions, you